let's learn a little bit about centripetal acceleration. So let's say I have a dot. It could be anything, and we're in deep space, so we're not going to think about gravity and all of these things yet. But let's say I have some object that's floating through space with some velocity. Let me draw the object. So it says this is its dot. And it has some velocity, and I will draw its velocity vector. Let's say that this is its, I'll draw it really big, because I have, oh no, that's not big. Let me make a thicker line. Whoops, there you go, thicker line. If you can see that. So let's say that's the dot's velocity vector. And I have a question for you. So this is what the dot's doing at exactly this moment. Let's say a little bit later, I want the dot to be doing something like this. I want its velocity vector to look like, I want actually its velocity vector to look like this. A little bit later. Oh, and its color changes to yellow. That's out of the scope. Color changing is out of the scope of this lecture. But let's say a little bit later, I want its velocity vector to look something like that. So I was a little careful because I want it to have the same magnitude, but just a little different direction. I want it to kind of tilt into the right a little bit. Let me draw that. And my question is, what had to be the acceleration acting when this was its velocity vector in order to get its velocity vector to look like this a little bit later? Well, right here, its velocity vector is completely in the x direction, right? And there's no y component. Let's break down this velocity vector into the x and y component. So its x component looks something like this, and its y component looks something like this. So in order to change its velocity, something would have had to, because clearly here its y component was 0. There's no y component. And now there is a y component. So the acceleration that you would have to apply to this dot would have to have some y component, right? The acceleration would have to have some y component. So let's say that. And this is acceleration. That's why it's not the same size. You might actually, let me draw acceleration in a different color. So it's, and I'll try to do this in a bunch of different ways so you get an intuition for it. I'm doing a slightly different blue. So you would have to accelerate in the y direction a bit, and we don't know how long, but long enough to get its velocity in the y direction this big. And then what would you have to accelerate in the x direction? Well, your x component shrinks a little bit, right? This was its x component, and now since you're tilted down, you get more y and less x. So what does the acceleration, what direction does the acceleration have to go in to shrink the x component? Well, you have to go opposite, right? So you're going to, acceleration is going to go that way a little bit. And so if you were to add these two vectors, you would have to accelerate something like, the acceleration vector would look something like this. The acceleration vector would look something like this. Right? So what I'm and this might be a little confusing to you, but all I'm showing is that I want you to think about when, and say an object is traveling through space at a constant velocity, what does the acceleration vector have to look like in order for that object to curve a little bit? So for example, if this was the, let me draw, let's say this object was here, right? And if we had no force on it, it would just keep moving in this direction. It would just, its path would look like this. Its path, I'll draw the path in brown. Its path would just look like this. It would be here, then it would be here a few seconds later. It would just keep going in the direction that it's at. And we know that from Newton's law. An object in motion tends to stay in motion. And the only way you can have a change in velocity is if you have some net force and some net acceleration on the object. So in order for the object to curve, in order for the object's path to look something like this, so here's the other path. Let's say the object's path is like this. And let's say it keeps curving. So the object's path is like that, and it keeps curving. So it goes there to there, and it's kind of going in a curved motion. What has to keep happening? Well, in order for the object's velocity to go from this direction, right in the x direction, in order for its velocity to go from this, you have to accelerate a little bit inwards, right? We drew that right here. You have to have kind of an inward acceleration. And now its velocity, and then if you did nothing else, then the object will just keep going in this direction. So in order to make it curve a little more, you gotta pull in a little bit again. So you have to have, and then if you don't pull in again, it'll just keep going in this direction. So you got to keep pulling inwards on it. You got to keep pulling inwards on it. And I think you're starting to get a sense of what I'm saying. So if you want the object to go into a circle, for example, there has to be a constant inward force always pulling on the object. Because if there isn't that constant inward, this whatever off-white color, this is when there's a constant inward force, the object's going to travel in a circular path, right? If that inward force, if that inward force doesn't exist, let's say that inward force is there, and then all of a sudden when the object's here, the inward force disappears. Then the object's just going to go in a straight line, tangent to the circular path. And that makes sense, and I'll go into it a little bit more detail in a second. But if you are spinning an object around in a circle on a string, and the string is providing the inward force, and as soon as you let go of the string, the object goes off in a straight line. And so that's what we're talking about. So what does this inward acceleration have to? Actually, before I go into actually calculating what that inward acceleration has to be, let's think about what happens if that inward acceleration isn't enough or if it's too much. So I just said if I have let's say this is like the center of our rotation. Let's say this is where the inward force is coming from, right there. And let's say this is my object. Let's say it's a spaceship. That's my spaceship. There's fire coming out of it. And actually, the fire would only go on an impulse, because once you have a little fire coming out in space, there's no wind resistance, so it'll keep just going. You don't have to keep. So these science fiction movies where the fire just keeps going, that doesn't make sense. You would just have an impulse of fire that would accelerate you, and then you wouldn't have to keep showing the fire in the back of the spaceship. But anyway, maybe you realize that already, or that's out of the scope of this lecture. But let's say the object's velocity is like that. And I don't know, let's say this is a planet or some kind of weird force field or something. If this force field is kind of a weak force field, if this object is moving really fast and this is a weak force field that's always pulling in towards it, the object's path is going to look something like this. It's going to look something like this. It's not going to be a circle. It's going to kind of spiral outwards, right? If this is so that's kind of a weak inward force. If it's a really strong inward force, the object's path is going to look like this, and I'll do that in yellow. It's actually going to fall in. It's going to spiral into the object. And if it's just right, given how far the object is, and I'll give you a formula for what just right implies, but if the inward force is just right, the object's going to essentially orbit around this object. It's going to go in a perfect circle. Its path will be like that. So let's think about what that inward force has to be. And we're not going to, this could have been gravity, this inward force, but I won't work with gravity yet, because gravity actually, the force changes depending on how close you get to it. So I won't deal with gravity yet, but it could have been anything. It's just a tractor beam. So let's try to get an intuition of how strong that inward force is and what variables is it dependent on. So let's say I have let's say this is my hand, and I have a string. I have a string, and on that string I have a rock. And my question is, if I want this rock to spin around in a circle, and it'll spin around in a perfect circle, we've all done this before. So if I want the rock to spin around in that circle, what has to be the force that I pull on this string? Or essentially, how much does the inward acceleration have to be on that rock? So let's get an intuition for maybe what has to happen. So think about it. If the rock is moving, let's say right here, at this point its velocity looks something like this. At this point its velocity looks something like this. And then when the rock is here, its velocity looks something like this. So to move from this velocity to this velocity, if the magnitude is really big, I'm going to have to apply more acceleration to change its direction. Hopefully that makes a little sense, right? To go from this velocity vector to this velocity vector, I have to if this vector was even bigger, if to say this vector looked like this, it had more magnitude, I would have to pull inward with even more force and accelerate inward at even a higher rate. So definitely, the higher the velocity, the more I'm going to have to pull in. And also, the higher the velocity, the shorter the time between this and this, right? This object's moving around the circle. So there's kind of two components that are affecting it on the velocity affects the acceleration I need in two ways. Oh, actually, I'm running out of time, so I'll continue this in the next video.